When solving a resistor circuit, there's a series of step-by-step procedures to follow that will allow you to get the current, the potential difference, and the power of each resistor, regardless of how many resistors are in the circuit. In this example, I'm going to work through a circuit that has 13 resistors that are connected to a 48-volt power supply. These same procedures, the same step-by-step method, will be used to solve any circuit with any number of resistors. So I'm going to take you through step-by-step how to solve a resistor circuit that has 13 resistors in it. This same step-by-step procedure is what you would do whether you have 5 resistors or 25 resistors. There are many little steps with little calculations, lots of room to make errors, but when we get to the end of it, we can check our work and become relatively confident that we have solved this circuit correctly, or we know that we haven't solved it correctly. So I know that my total voltage is going to be the battery voltage. So if my battery voltage is 48, that's going to be my total voltage. We have to find the total resistance and then get the total current and the total power. We're going to do this in a step-by-step fashion where we'll take any 2 resistors or 3 or 4 resistors that we can combine to get an equivalent resistance. Whenever resistors are in series, we can add their resistances together and replace those resistors with a single resistor having the sum of the individual resistors for its resistance. When resistors are in parallel, we replace them by adding reciprocals of those resistances and then taking the reciprocal of that. We can do this in one step at a time, combining any 2 or 3 at a time, or we can skip steps and combine resistors, in the same step. So that's what I'm going to do here. I can see resistors 3 and 4 are in series, so I can replace them with an equivalent resistance that's equal to 6 ohms plus 8 ohms. So I can replace these 2 with a 14 ohm resistor. Resistors 5 and 6 can be replaced. 8 and 10, I can replace those 2 with an 18 ohm resistor. Resistors 10 and 13 can be replaced. 2 ohms and 8 ohms gives me 10 ohms for those 2. And then I can also take the 2 that are in parallel, resistors 11 and 12, and replace them with 1. Now when they're in parallel, we add reciprocals and then take the reciprocal of that. Since they're both 7 ohms, I know my equivalent resistance will be half of 7, or 3.5. On a calculator, I would go 7 reciprocal plus 7 reciprocal equals, and then take the reciprocal of that for my 3.5 ohms. Now, I need to redraw my circuit with these resistors in place. So I've got my battery, 48 volts. I've got resistor 1, which still has 4 ohms. And then when I get to this part, I leave resistor 2, which is 9 ohms, but I replace 3 and 4 with a 14 ohm resistor. And then I get to this section, I replace resistors 5 and 6 with an 18 ohm resistor. I still have number 7 with 9 ohms, and I still have number 8 with 12 ohms. Then when I get to this part, I split, and on the right path, I combine resistors 10 and 13 with my 10 ohm resistor. I still have resistor 9, which is 4 ohms, and then I have my 11-12 combination, which is 3.5 ohms. They join back together and then go back to our battery. In my next step, I can combine these two, these three, and these two. So when I combine the 9 and the 14 that are in parallel, I have to add reciprocals. So 9 reciprocal plus 14 reciprocal equals, then take the reciprocal, I get 5.48. So those two make 5.48 ohms. I do the 3 in parallel the same way. 18 reciprocal plus 9 reciprocal plus 12 reciprocal equals, take the reciprocal of that, I get 4. So all of those are replaced with 4 ohms. And then these two are in series, so I replace them with a 7.5 ohm resistor. So I'm going to redraw my circuit now. I've got my battery. I still have my 4 ohm resistor, which is resistor 1. I've got now a 5.48 ohms. And that we'll call resistor 2, 3, 4. Then I have 5, 6, 7, and 8 combined for 4 ohms. So that's resistor 5, 6, 7, 8. And then I've got a parallel branch here with a 10 ohm resistor and a 7.5 ohm resistor. Now that 7.5 is resistor 9, 11, 12, so resistor 9, 11, and 12. The notation can be anything you want. It can get kind of messy. In my next step, I could go ahead and combine these three in series, but I'm going to wait and I'm just going to combine these two first. So I've got a 10 ohm and a 7.5 ohm in parallel. So 10 reciprocal plus 7.5 reciprocal equals, and take the reciprocal, 4.28 or 4.29 ohms if I round off. So my very last circuit, I combine all 4 of those that are in series, 4, 5.48, 4, and 4.28. And so I go 4 plus 5.48 plus 4 plus 4.28. And I get 17.76 ohms, and that is my total resistance. So my total resistance is 17.76 ohms. My total current will be total volts over total resistance, so 48 divided by 17.76 gives me 2.70 amps. I multiply that 2.70 amps times 48 to get my total power, 129.6 watts. So power in watts is V times I, potential difference in volts times current in amps. So this final resistor has a current 2.7 amps and it has a voltage of 48 volts. In order to get the values of the individual resistors, I work backwards. You say, where did this resistor come from? Well, it came from this circuit where these were all in series once we replaced that with the 4.28 ohms. So you say, well, what stays the same in series? Well, it's current. If there's 2.7 amps going through here, we're going to have 2.7 amps in each of these sections. Well, that 2.7 amps going through resistor 1 can go in our chart. For the others, we have to find the voltage. So volts is V times I, volts is V over R. So 2.70 amps divided by 4 gives me V is I times R, excuse me. So getting the volts, I times R, 2.70 times 4 gives me 10.8 volts, which can go in my chart. I'm going to have 2.7 amps times 5.48 ohms here to be 14.80 volts. 2.7 times 4, again, is 10.80 volts. And 2.70 times my 4.28 is 11.56 volts. So we've already solved resistor 1. We're finished with it. Resistors 2, 3, and 4. You say, well, where did this resistor come from? Well, it came from these two. How are those two arranged? Well, they're in parallel. What stays the same in parallel? Volts. So if this is 14.8 volts, if we replace it with two resistors that are in parallel, they'll each be 14.8 volts. So we have 14.8 volts here and 14.8 volts there. Well, that's number 2, 14.8. 14.8 volts for resistor 2. So we can find the current through resistor 2, V over R, so 14.8 divided by 9 gives me 1.64 amps of current. And then we're finished with resistor 2 after we calculate the power. So then the current through the 3-4 part, V over R, 14.8 divided by 14 is 1.06 amps of current. And then you say, well, where did this resistor come from? It came from these two that are in series. What stays the same in series? Current. So each of these will be 1.06 amps. 1.06, 1.06. Then we can multiply the 1.06 times 6 to get 6.36 volts for that one. And 8 times 1.6 should be 8.48 for the second one. Or, no, 6 times 8 is 48, right? Okay, so we've solved numbers 3 and 4. You can go to this one. So that's this resistor, 5, 6, 7, 8 combo. 4 ohms, 2.7 amps, 10.8 volts. Where did this one come from? It came from these three. How are those three arranged? Parallel. What stays the same in parallel? Volts. So this is 10.8 volts, 10.8 volts, 10.8 volts. So that's number 7 and number 8 each have 10.8 volts. I can get my current, 10.8 divided by 9 is 1.2 amps, and 10.8 divided by 12 is 0.9 amps. So now I have volts and amps for these two. But this resistor, 10.8 volts, 18 ohms. So if I go 10.8 volts divided by 18 ohms, I get 0.6 amps of current. So you say, well, where did this one come from? It came from numbers 5 and 6 added together. How are they arranged? Series. What stays the same in series? Current. So if this is 0.6 amps, then there's 0.6 amps through each of these, 5 and 6. So 0.6, 0.6. So when I multiply current times resistance, that will be 4.8 and 6.0 volts. So the only thing we have left is the 9, 10, 11, 12, this section here. So that's this resistor. The 4.28 ohms, 2.7 amps, 11.56 volts. It came from these two that are in parallel, so each of these will be 11.56 volts. If I take V over R, 11.56 divided by 10, I get 1.16 amps. And if I take 11.56 divided by 7.5 ohms, I get 1.54 amps. Where did this come from? It came from 10 and 13 that are in series. What stays the same in series? Current. So 1.16 amps for number 10 and number 13. So this will be 2.32 volts, and 8 times 1.16 is 9.28 volts. So now we look at this one. It's 1.54 amps, 7.5 ohms, 11.56 volts. Where did it come from? It came from these two. How are they arranged? Series. What stays the same in series? Current. So this is 1.54 amps, this is 1.54 amps. Well, that's number 9, 1.54 amps of current, 1.54 times 4 gives me 6.16 volts. So now I only need 11 and 12. Well, they're in parallel to combine for 3.5 ohms, so voltage of the 3.5 ohm resistor will be the same voltage for each of those. So 1.54 amps times 3.5 ohms is 5.39 volts. So number 11 and number 12 will both be 5.39. So when I do their currents, 5.39 divided by 7, we get 0.77 amps. Now to finish the chart, I just multiply V times I. You can do this as you go along, or you can wait till the end like I'm doing, but 10.8 times 2.70 is 29.16, 14.8 times 1.64 is 24.27, 6.36 times 1.06 is 6.74. You could also put these values into Excel and have a column for power that just multiplies those and save yourself these calculations. 8.48 times 1.06 is 8.99. 4.80 times 0.6 is 2.88. 6 times 0.6 should be 3.6. 10.8 times 1.2 is 12.96. 10.8 times 0.9 is 9.72. 6.16 times 1.54, 9.49. 2.32 times 1.16 is 2.69. 0.77 times 5.39, 4.15 twice, and then 9.28 times 1.16 is 10.76. So now we've completely solved the circuit. We have the potential difference across each individual resistor, we have the current through each resistor, and we have our total power. There were a lot of calculations there, a lot of places to mess up. So how can we have any confidence at all that we're correct? Well, just getting to an answer is an accomplishment in itself, but there are 3 ways that we can check our work. The first is to add up all the individual powers and see if they equal the total power. So I'm going to do that. 29.16 plus 24.27 plus 6.74 plus 8.99 plus 2.88 plus 3.60 plus 12.96 plus 9.72 plus 9.49 plus 2.69 plus 4.15 plus 4.15 plus 10.76 hopefully gives me something close to 129.6, and I get 129.56. So it's highly unlikely that all those powers would add up to equal your total power if you made mistakes in the table. So I can be relatively confident that it's correct. The other two ways of checking your work are to use principles known as Kirchhoff's laws, Kirchhoff's loop law and Kirchhoff's circuit or junction law. I have other videos that describe those laws and show how you can use those laws to also check your work. But keep in mind, you cannot expect to add up all the voltages to equal 48. That is not one of the checks. It's only the power that all of the individuals add up to equal the total.